the beginnings of geometrical representations and calculations.
Welcome to the deep dive. You've shared some fascinating material with us, and our mission, well, it's really to boil it down, find those core insights, those surprising bits that give you a shortcut to being, really well informed. Think of it as your personal exploration.
And today, that exploration takes us way back
Yeah.
to the very beginnings of geometrical thinking. We're looking at how primal societies and then those big river valley civilizations, Egypt, Babylonia, first started to think about shape and form and, well, calculation.
Exactly. And this isn't just about, listing dates and facts. We want to uncover the really remarkable ways these early humans used geometry long before it became like formal math.
How their everyday lives, their rituals, their whole view of the world was tangled up with these geometrical ideas.
So how are we figuring this out? What are we working with?
We've got a pretty good mix, actually. Academic stuff, looking at archaeology, analyses of historical records, papyri, clay tablets, and some really interesting interpretations of old artifacts.
Okay, let's start way back then. Primal societies. It's kind of amazing. The source mentions geometrical decoration on clay pots from maybe 40,000 BC.
40,000, yeah, it's staggering. And these weren't just random doodles. The patterns, things like folded strips or maybe 6 circles around a central one, like they found from Cretan culture, they were often specific to certain groups.
So like a signature style.
Pretty much. Prehistorians can actually use these fragments, these decorated bits of pottery, to trace how people moved around. It's like a silent geometrical map of migrations.
Incredible. Not just decoration, but cultural markers. And
Right.
what about shapes? Did they notice basic shapes?
It seems so. The text suggests things like equilateral triangles, squares, and that implies understanding right angles, which is a big step.
Right.
And regular hexagons, they weren't just, background noise. They sparked interest, maybe even a kind of playful curiosity, the first little nudges towards thinking about shapes theoretically.
Like, all the sides are the same, that sort of thing.
Exactly. And then practical needs really pushed things along. Think about it, digging ditches for water, building dams, laying out houses, even just figuring out who owns which bit of land.
Yeah, basic survival stuff.
All that requires some grasp of geometrical ratios. Maybe intuitive at first, trial and error, driven by what worked, before they started thinking logically about why it worked.
And it wasn't just flat 2D stuff, was it? Building requires thinking in 3 dimensions.
Oh, absolutely. You can't build a hut or, later, grander things without understanding basic solids. Cuboids, cubes, pyramids, columns, essential stuff.
And they looked up, too. The source mentions stars.
Yeah, looking at the stars, figuring out patterns in the night sky, that likely led to the idea of a spherical triangle. Geometry on a curved surface.
Mind-bending. Okay, so the sky's a geometry lesson, too. What about something simple, like cutting a square in half?
My section, yeah. Like drawing a diagonal across a square, a rectangle, or a diameter through a circle. The source makes a good point. Pre-Greek cultures definitely knew these relationships and used them practically.
But the Greeks were different how?
The Greeks wanted to prove it. They wanted the why. They built this whole logical system, axioms, proofs, leading up to Euclid and his elements. The earlier folks were more focused on the how-to.
Application versus theory, in a way.
Kind of. Though the lines can be blurry, and geometry wasn't just for building and land. It seems to have soaked into their culture.
How so?
Well, the source says basically every culture we know weaves in geometrical elements somewhere. Religious ideas, shape designs for jewelry, the shape of altars, even how people danced in rituals. It's everywhere.
Which sounds like it connects to this idea of ethnomathematics. What's that about?
It's a field that tries to uncover the mathematical ideas embedded within cultures, especially early or indigenous ones. And sometimes the findings are, well, stunning.
Like what?
There's this Angolan tribe mentioned, their creation myths, their stories about how the universe began. They express them through these incredibly complex drawings made with a single continuous line.
One line. Wow.
Yeah. And to get the symmetry and patterns right, freehand, requires a really deep, maybe unconscious grasp of geometry.
Yeah.
It suggests this fundamental human way of thinking geometrically, encoding ideas in shapes.
So geometry is literally part of their storytelling. That's powerful. And speaking of observation, you mentioned stars, but also shadows, sundials.
Right. Watching a shadow move from a stick, a stone, whatever across the ground during the day through the seasons, That's basically mapping the sun's path. It naturally gets you thinking geometrically.
And that leads to actual structures, like the Goseck Circle.
Exactly. Goseck Circle, Germany, around 4800 BC, it's thought to be the earliest known solar observatory. We're talking huge concentric ditches, wooden palisades, with gateways lined up precisely with the solstices, sunrise and sunset on the longest and shortest days.
So vital for farming, I guess, planting times.
For sure. Knowing the seasons was crucial, but probably cultural ritual uses too. It's like this combination of calendar, community center, and sacred space nearly 7,000 years ago.
Which makes you think of Stonehenge, obviously, but that was later.
Yeah, Stonehenge is much later, maybe 2,000 years or so after Goseck. 3rd, 2nd millennium BC, also seen as a solar observatory, a ritual site.
But maybe more than just lining up stones. Geometry involved?
Some research suggests so. Basic geometrical ratios might have been used in the layout. And there's this intriguing idea, about the Pythagorean theorem.
Really? At Stonehenge?
Possibly. Using something like a rope with knots tied at specific intervals to make a 3-4-5 triangle, that gives you a perfect right angle. Imagine using that simple tech for such a massive construction.
A prehistoric T-square. And what about Woodhenge?
Woodhenge, yeah. Timber circle nearby around 1800 BC. There's a claim, maybe a bit speculative, that they used a more complex Pythagorean triangle there, 12, 35, 37.
Wow. That's specific.
It is. Highlights how much geometry they might have known. And around the same time, maybe a bit earlier, you get the Nebraska disc.
Oh yeah, the bronze disc with the gold symbols.
That's the one. Some see it as an early map of the stars, maybe the Pleiades cluster, but it's still heavily debated exactly what it represents.
So, okay, clearly these early societies, even before the big empires, were doing some serious geometrical thinking.
Absolutely, from pot patterns to stone circles, which sets the stage nicely for the more organized societies in the river valleys.
Right. Let's start briefly with the Indus Valley Harappa Mohenjo-Daro. What do we see there, geometrically speaking?
Well, with the Indus civilization, roughly 3000 to 2000 BC, you see this amazing standardization. Bricks made in consistent 1.2.4 ratios.
That's very precise.
It is. And street layouts like grids, very planned, standardized weights too, all suggest practical geometry in city planning, construction, trade. The big problem is we can't read their script.
Ah, so we see the results but not the instructions, basically.
Exactly. We see the geometrical thinking in the ruins, but the why and how is still a bit of a mystery.
Okay, but when we get to Egypt, the picture gets clearer. Because of writing.
Much clearer, yeah. Hieroglyphs start appearing around 2900 BC. And we have these incredible documents, especially the Rhine mathematical papyrus and the Moscow mathematical papyrus from the Middle Kingdom, maybe just after 2000 BC.
What are they?
They're basically handbooks, collections of math problems with solutions, probably used to train officials, scribes, people who needed to manage things, and they're long, like over 5 meters each, packed with problems.
So, serious teaching tools. How did they draw geometry, though? You said no perspective.
Right, no perspective. Like we think they usually showed solids using a top view plan and a side view elevation. The source has this great example, drawing a rectangular pond with trees around it. The trees are sort of folded out flat to the sides.
Huh. A different way of seeing or showing 3 dimensions.
It works in its own way. And surveying land was a really big deal, especially for temples.
Ceremonial, almost?
Definitely. Often done by the pharaoh himself or high priests. We even find these geometric amulet instruments, suggesting a sacred aspect to measuring and building. And for big projects, they apparently drew full-size plans, top and front views, right onto stone surfaces.
Actual blueprints in stone. Cool. Now, calculations. Their formula for a 4-sided shape area sounds rough.
It was an approximation for sure. They'd average opposite sides and multiply the averages. So sides A, B, C, D area is roughly A plus C2 times B plus D2.
Okay.
And the really interesting bit, for triangles, they just used the same formula but left out the non-existent fourth side. Probably because they didn't have a concept for zero.
So they just ignored it. Pragmatic. What about circles? Their area method sounds really unique. Something about subtracting a 9th.
Yeah, it's peculiar. Take the diameter, subtract 19th of it, and square what's left. So area equals 89 diameter 2.
Does it even work?
Amazingly well. It gives a value for pi of about 3.16, which is remarkably close, and we have no idea how they figured it out. No derivation found.
Just found it, maybe through measurement.
Possibly. Problem 48 in the Rhine Papyrus shows a square being turned into an octagon by snipping the corners. Some think this visual process, approximating a circle with an octagon, might have somehow inspired the formula.
A visual shortcut to a good answer? Clever. And they calculated volumes, too. For granaries and things?
Oh, yeah. Especially cuboid and cylindrical containers. They used their circle area approximation for the cylinders, and they seem to have thought of volume as stacking layers, the layer measure idea,
Yeah.
base area times height.
Makes sense. But what about pyramids? They built the biggest ones. Surely they had a volume formula.
You'd think so.
Yeah.
But incredibly, no explicit formula for the volume of a pyramid has been found in any Egyptian text. And it turns out a proper proof for V equals 13 base height actually needs calculus concepts, which Max Dan showed much later.
So they built the Great Pyramid without knowing the formula we learn in school. How?
Practice, experience, good rules of thumb. It's humbling, isn't it? But wait, the Moscow Papyrus does have something pretty advanced. Problem 14. It gives the correct formula for the volume of a truncated pyramid. A pyramid with the top sliced off parallel to the base. V equals H3. A2 plus AB plus B2, where A and B are the side lengths of the square top and bottom.
That looks complicated. Did they use it much?
Doesn't seem like it was widespread. They often used a simpler approximation. Average the top and bottom areas and multiply by the height.
Like their quadrilateral formula.
Exactly. And Kurt Vogel, a historian of math, had this interesting idea. Maybe they realized their simple approximation wasn't quite right through measurement, and they sort of intuitively added a middle term, this AB part, representing a kind of average area.
And stumbled onto the right answer.
Possibly. It suggests mathematical discovery isn't always neat theorems and proofs. Sometimes it's messy, empirical, intuitive leaps.
Fascinating. Okay, let's cross the desert to Mesopotamia. Babylonia. You said their sources are even richer.
Yeah, thanks to durable clay tablets with their cuneiform script, we have loads for the old Babylonian period, maybe 1900 to 1600 BC. Math kind of plateaued a bit after that, until the Seleucid era when astronomy really pushed it forward again.
And their math was also practical.
Very much so. Economy, trade, building, astronomy, all needed math. And arguably, they reached a higher level, mathematically speaking, than the Egyptians, especially in algebra-like methods.
And the big one, they knew the Pythagorean theorem, way before Pythagoras.
That was a huge discovery, found in texts analyzed around 1916. They used it frequently. We find tablets with field plans, house layouts, technical drawings for canals with calculations explained.
Like manuals.
Pretty much. They even used everyday words for some technical terms, which is kind of nice. It makes it feel grounded. But it wasn't all practical.
Theoretical stirrings.
Seems like it. We see drawings exploring areas of regular polygons, suggesting some theoretical interest. And they develop methods that look a lot like early algebra. Plus, their use of Pythagoras for rectangle diagonals is constant.
Did they have trouble if the diagonal wasn't a whole number? Square roots?
They often picked numbers, so it worked out nicely, Pythagorean triples. But they did have methods to approximate square roots when needed, using iteration, similar to what we call Hero's formula.
That problem about the bar leaning against a wall that uses square roots?
This does. It's a classic application of Pythagoras. A bar leans, it slides down a bit. How long was it originally? It pops up everywhere. Babylonian texts, Chinese, Indian, medieval Europe. A truly universal math problem.
Some problems just stick around. What about dividing land? That must have been common.
Definitely. They had methods to divide, say, a four-sided field into two equal parts with a dividing line. The formula they used involved square roots of the squares of opposite sides. It was an approximation, really.
How so?
It kind of ignored the other two sides, but it worked okay for shapes that were roughly rectangular or trapezoidal. Good enough for practical purposes, probably.
Practicality rules again. And circles. Did they do the diameter thing like the Egyptians?
Nope. Different approach. They worked from the circumference. Their formula for area was A circumference squared, divided by 12.
C squared over 12. Where does that come from?
Well, they often approximated the circumference C as 3 times the diameter D, or C equals through D. Since D equals 2R, that's C 6R. If you plug C6R into A equals C212, you get A 6R212 equals 3 6R2, 12 equals 3R2.
Ah, A equals 3 per 2. A different approximation for pi, effectively pi 3.
Exactly. Maybe they got it from thinking about an inscribed hexagon, whose perimeter is 6R, or maybe averaging inscribed and circumscribed squares. It's another distinct way of thinking about circles.
It's amazing how they reached different methods. Did they do more with circles? Segments?
They did. They worked on circle segments. They had formulas to calculate the sagitta, that's the little height bit of the segment, and the chord length based on the diameter.
That sounds quite advanced, like early trigonometry.
Definitely early chord geometry, stuff that Hipparchus and Ptolemy would develop much later. But crucially, they didn't seem to have a general concept of an angle. They understood right angles implicitly, but not angles in general.
Interesting limitation. What about slopes, like for building ramps or dams?
They had a neat practical method. They described the slope by its redown by 1 cubit, basically, how much horizontal distance you cover for every 1 cubit you go up vertically.
Yeah,
Like run over rise, but fixed rise.
very practical. And 3D shapes, volumes.
Cuboids, prisms, cylinders, no big problem. Using base area times height, sometimes with their approximate area formulas if the base was circular.
But pyramids.
Same story as Egypt. No general pyramid volume formula found in Babylonian texts either. And for truncated pyramids.
Did they have the fancy Moscow papyrus formula?
Nope, they seem to use the same simpler approximation as the Egyptians generally did, averaging the top and bottom areas times the height.
Huh. So some shared knowledge or parallel development there.
Seems likely, though.
Mm-hmm.
There's one text, BM 8519428.
Yes.
They might contain something very close to the correct truncated pyramid formula, V equals H3, A2 plus A plus B2. It depends on whether a factor was left out because the specific numbers in the problem made it equal to 1. It's tantalizingly close.
A mathematical what if? What about cones with the top cut off?
Cone frustums, yeah. They calculated the volume using an averaging formula. Half the sum of the top and bottom circle areas times the height, another approximation.
And always the Pythagorean theorem lurking.
Oh, yes. Which brings us neatly to that very famous tablet, Plimpton 322.
Right. The one people thought was a trig table.
Exactly. That was the initial, very exciting interpretation by Neugebauer and Sachs back in the 40s. They saw the columns of numbers as relating to secant squared or tangent squared, basically listing parameters for integer-sided right triangles. Trigonometry, 1,500 years before the Greeks usually credited with it.
That would be huge, but not the current view.
Well, it's been seriously challenged. More recent work, especially by Eleanor Robson, puts it in a completely different context. She looked at where it was found, other texts from the same place, Larsa, around the mid-18th century BC, and she argues it fits much better as a teaching tool. A list of problems, or parameters for problems, involving Pythagorean triples, may be used for training scribes in calculations related to land or construction, things needed for the bureaucracy, not abstract trigonometry.
So more about practical problem solving using triples, less about theoretical angles.
That's the current thinking, largely. It's still an amazing tablet, a unique, highly organized list of Pythagorean triples linked by this mathematical relationship. But probably not trigonometry as we know it. It shows how interpreting these ancient artifacts can change.
Definitely. Wow, okay. We've covered a lot of ground, from cave paintings to clay tablets. So pulling it all together, what are the big takeaways?
For me, it's seeing just how deep the roots of geometry go. It wasn't just invented by the Greeks out of nowhere. You have this long, slow burn of practical understanding, intuitive grasp, developing in primal societies out of necessity, out of art, out of watching the sky.
Right, driven by life itself.
Exactly. And then in Egypt and Babylonia, you see these sophisticated systems emerge, focused on practical calculation, finding clever approximations, tackling real-world problems, different approaches sometimes, but laying so much groundwork.
Yeah, the big aha for me is that shift in perspective. Geometry wasn't just one invention. It's this ancient, cross-cultural human endeavor with roots stretching way, way back. The Greeks formalized it, but they built on millennia of practical knowledge.
Absolutely. And maybe a final thought to leave you with. If these early geometrical ideas grew directly from observing the world, from building things, from dividing land, does our modern math, which can feel so abstract sometimes, still have that strong connection? Are there fundamental ways of understanding shape and space tied to the physical world that maybe we overlook because we rely so much on complex formulas? It makes you wonder about the very nature of mathematical thought.
That is a great question to ponder. Maybe time for all of us to look a bit closer at the geometry hidden in the world around us. Thanks for joining us on this deep dive.